All right, this is going to be our one example that I'm going to do for you, but it's going to be kind of in depth. Using Bernoulli's equation and the continuity equation to help us understand fluid flow. So if we look at these equations, these are the bottom two, F5 and F6, that deal with fluids. The continuity equation says the volume flow rate at any 2 points in a closed pipe has got to be the same as long as the pipe is full. So that's the cross-sectional area times the velocity at one location is equal to the cross-sectional area times the velocity at another location. Hopefully it makes sense. If you've got a skinny pipe, you've got to be going faster to have the same amount of fluid flowing per minute or per second as you do in a wide pipe where it will be flowing slower. Oftentimes you have to use this to find velocities, which you would then use down here in this Bernoulli's equation. So part A is going to ask us the speed at the start of the pipeline. So this is a gasoline pipeline, and the density of gasoline was given to us, although you might have to look it up in the textbook. If it was a textbook problem in the AP, they would probably give you just a density variable, and you would have to plug variables into an equation. At any rate, it's transporting fuel over a hill. The diameters of the pipeline are shown, as is the gauge pressure and speed at the top of the hill. So this gauge pressure is 40 kilopascals. The speed is 2 meters per second, diameter of 0.4 meters here, diameter of 1 meter right there. So at this particular point, the first part of this is really simple. The second part we'll do over here. We're just asked to determine the speed at the start of the pipeline. So that's this V1. So when I think about this, I'm going to just simply write down my continuity equation. That's fantastic. And the lowercase v means velocity, uppercase V in this topic means volume. So the question might be, well, how do you get this? If you want to get the actual area of this, which you might, you would have to do pi r squared. If you recognize that these are going to be proportional to the square of this, you could do 1 squared times V1 is equal to 0.4 squared times V2. You wouldn't have to get the exact value. If you want to know the specific volume flow rate, you would have to use pi r squared times V1 and pi r squared times V2. So I'm going to set that up so you can see what that looks like. So that's going to be pi r, which is 0.5 meters here. That's a little bit over. There we go. Hopefully you can see that. 0.5 meters is half of this 1 meter diameter. Times V1 equals pi. 0.2 meters is the radius. V2. It's 2 meters per second. Well, you notice, it's got to be squared. You notice that the pi's cancel out, which is a shame because pi is delicious. In this case, I end up 0.5 squared, which is 0.25 times V1. Point 2 is 0.04 squared. 0.04 times 2. So again, this becomes 0.08. 0.08 divided by 0.25 gives me a really low speed. V1 is 0.32 meters per second. 0.08 or 0.25. So that's the speed just going here. Should make sense, it's a lot wider, so it's going to go a lot slower. The second part of the question, and I'm going to have to move this out of the way, but we are going to use Bernoulli's equation. The second part deals with determining the absolute pressure at the start of the pipe. So there's going to be a few tricks in this. Absolute pressure I'm writing so much I'm going through markers. All right, So basically what that's saying is we're going to have to find this P1. So we got a lot of stuff here. I'm going to write down the general formulas first, and then we're going to go from there. So I've got P1, which is what I'm shooting for, plus rho g h1. I'm not sure if that's h1 or if it deals with y1 on that formula sheet. Plus 1/2 rho v1 squared is equal to p2 plus rho g h2 plus 1/2 rho v2 squared. Looks like a lot of stuff, but just knowing this fills in 4 of those variables, which is pretty interesting. So I'm going to go here and fill in what I know right now. Well, there's other things we can do to simplify things. For example, this shows a 30-meter height between the bottom and top of the pipe. Technically, I guess it should go from center to center, but I'm not going to worry about that. What that means is if this is location 1, H1 is at the bottom, we can choose what numbers we would use for our heights compared to the ground level. I'm going to choose that as 0. That means that if this is 0, that whole term goes away. And this becomes 30 meters over here. So now I'm getting things a little bit simplified. So I'm going to say P1 plus 1/2 density of 680 kilograms per cubic meter. V1, which we found out was 0.32 meters per second, squared, is going to equal P2, which is 40 kilopascals. Now the problem is that's gauge pressure. I thought I said that. I might not have. So that is P gauge. What we need to think about is whenever we're doing these calculations, we have to think about absolute pressure. So in this particular case, let's tilt that a little bit over there. In this particular case, I need to figure out what that is. Well, atmospheric pressure, according to your textbook, is 101,300 pascals. So we're going to say that this is 101,300 plus 40,000, because 40 kPa, kilopascals, is 40,000 pascals. So that's going to be 141,300. So what actually I'm going to do now is I'm going to shorten this left side of the equation so it can expand on the right side of the equation. So I've got 600.32 squared times 680 times 0.5, and that gives me about 34.8. P1 plus 34.8 equals, now I'm going to go to green, put everything on the right side over there in green. So I started with that, and I've got to do these things as well. That's going to equal 141,300. So what it says is this is a very small effect, that kinetic energy when your speed is so slow, plus 680, 9.8, height is 30 meters, plus, so this is now this term I'm putting down here, 1/2, 680, should have put units with it, but I was hoping to fit everything over here, 2 meters per second squared. So when I go back, I'm going to get P1 plus 34.8 equals 141,300 plus this 680 times 9.8 times 30. It's going to be 199,920. 2 squared is 4, times 1/2 is 2. 2 times 680 is going to be 1,360. So notice the kinetic energy on both sides Doesn't do much, which is interesting that the speed changes. If the speed changed more, I think it would matter. So when I want to solve for P1 now, P1 plus 34.8 equals a lot on the other side, 342,580. So obviously the 34.8 doesn't mean much. So P1, 342, 545.2. That is the absolute pressure at P1. But I'm asking to find, oh, I did ask to find that. If I was asked to find the gauge pressure at that, I could say P gauge equals 342, 545.2 minus 101, 300. And this really should be rounded. I forgot that that's where I was stopping, so I will end up rounding that. We'll say this is going to be 342, 500. We're going to round that to 342, 500. 342 minus 101 is 241. .2 kilopascals. That would be the gauge pressure. This is absolute. So that's how you go through a Bernoulli's problem. All right, these are the last parts of the Chapter 13 lecture. Deals with fluids, pressure, and density. And these examples are going to deal with density. So again, you can remember the general formula of density is P equals mass over volume. One thing you may need to know, and the formula for volume of a sphere is actually on part of your formula sheet. I'm pretty sure about that. I hope, I think, maybe. Yeah, it's over here on this part with geometry and trigonometry and things like that. So that's 4/3 pi r cubed. So sometimes they might give you the diameter or radius of a sphere, and then you've got to go and figure out the volume of it using that 4/3 pi r cubed, and then work that into a density equation. At any rate, we're going to go over here. This is a problem that's somewhat similar to ones I've seen on AP exams or questions. So it says a flat slab of styrofoam with a density of 32 kilograms per cubic meter floats on a lake. I don't think there's supposed to be a comma there. At any rate, what volume is needed to have a 40 kilogram girl on the styrofoam without it sinking? So in other words, her mass plus the mass of the styrofoam need to be supported by a certain volume of styrofoam. So conceptually, the way I would like to think about this is that for you to float, you need to have balanced forces. You would essentially need to have something like this, where you would have the buoyant force, the gravitational force. Those two would be equal. So I'm going to say force up equals force down. Hopefully that makes sense. And that means that force buoyant is equal to the force of gravity on girl plus F grav on styrofoam. I'm a little trademark symbol there. I don't know if it's trademarked anymore or not. So those two things. So to figure out the buoyant force, we're going to go back to this. That's the volume of the liquid multiplied by the density of the liquid multiplied by G. That would equal the weight of the fluid that is displaced. So that's going to go over here. And we're going to say on a lake, so that's water. And then this is going to be mg and girl times g plus gravity on styrofoam mg. How do I find the gravitational force on the styrofoam? Well, I know the density equation. Mass is equal to volume times density. So it's going to be basically density of the styrofoam, V. But the volume of the water displaced will equal the volume of the styrofoam. So rather than saying this is being different, it really would be the same as the volume of the water. So those two V's could be the same. I don't know if I should put that as a styrofoam or not, since it's the same volume. I'm actually going to put that as the volume of the water displaced. No. And then G. So something like that. So let's go and put some numbers in over here. I'm going to say 1,000 kilograms per cubic meter. Don't know the volume yet. G is 9.8. It really is going to be one volume, so I'll do that. Her mass was 40 kilograms. 9.8. Plus the density of styrofoam is 32. That volume, same as the volume over here, times 9.8. So I've got an unknown over here and an unknown over here, but since we know the volume of the water displaced would equal the volume of the styrofoam, it's the same variable. So I get 9,800 V. 40 times 9.8 is going to be 39.2, 392. 32 times 9.8, I don't know, it's a little less than 320. 313.6. So then I algebraically move that over here, subtract it from both sides, and I get that the volume is going to be quite small in this case, 0.041 cubic meters. So styrofoam has a really low density, so it doesn't take much of it to support that mass and the 392 newtons of weight from that girl. So that's that version of the problem. Over here, we're going to take a look at this second one. So I'm going to move this in front of this side so I don't get distracted. We've got a container of water, it looks like a beaker, and there's a plastic sphere here, so it might be something you would buy at like a craft store, and it's held on by a rope. And there's tension. How do I know that it's held on? Well, if water's density is 1,000 kilograms per cubic meter and the plastic's density is 840 kilograms per cubic meter, then if I cut this string, that would float up to the top, and part of it would be above the surface of the water until it came into equilibrium. That is a little bit better right there. So we want to find the tension holding in the string that's holding this plastic sphere. So in this case, once again, I'm going to think about a free body diagram here. So I've got a force upward. That's a buoyant force, which is really the weight of the water, or the water acting on the plastic sphere. I've got a force downward, which is actually going to be force gravity on plastic. And again, this is going to be larger than this, so if we cut that string, the plastic would end up accelerating upward and end up floating. So since this isn't doing that, there's got to be tension in the string. That is also acting downward. So this amount of force would equal that amount of force. So again, I can think about a force up equals a force down scenario. In this case, it's buoyant. It's going to equal F grav plus tension, or force of tension. So essentially, I'm turning my free body diagrams into these mathematical equations. It really helps me to visualize that first. So one of the things I've got to do here, then I'm going to put this in terms of equations. I'm going to say that this is going to be the density of water times the volume of the water that's displaced times G. This is going to be the mass of the plastic times the volume of the plastic. But again, these two are going to be equal. Actually, hold on for a minute. Nope, that's just the mass of the plastic times G. Now I'm going to have to get that by figuring out the volume and the density. And that's what I'm trying to find. That tension is the holy grail of the things that I am looking for here. So now off to the side, I've got to figure out something, which is really the volume of this. So when I look at it, volume is 4/3 pi r cubed. That's 75 cubic centimeters. I've got to convert that into cubic meters. You should be able to do that using your phone app or your graphing calculator. So that volume is equal to 7.5 times 10 to the negative 5th cubic meters. Actually, I don't need to do this. Sorry about that. I need to do something else, though. I need to figure out the F grav is equal to density of plastic times the volume times G. Hopefully you can still see me over here. It's just I'm running out of space. So F grav, the density is 840 kilograms per cubic meter times the volume, which I had up here, 7.5 times 10 to the negative 5th times 9.8. So F gravity on the plastic is going to be 0.6714 newtons. Nope, I lied, 6174, because apparently dyslexia. Okay. This is going to be the weight of the water displaced. This is going to be the weight of the density. The tension is going to be the difference between the two. So I guess I could have probably done this a little bit more over here. But once again, if we use our density formula and we rearrange it, volume times density would equal mass. So essentially I'm getting that mass up here by using volume times density. That really is mg. So in this particular case, density of the water, 1,000 kilograms per cubic meter. Volume is the same because it's completely submerged. 7.5 times 10 to the negative 5th cubic meters, 9.8 equals this, which I came up with is 0.6174 plus tension. Now notice the way that I did this, I wish I just would have made more space. This is rho Vg for water, this is rho Vg for plastic. So essentially, if I did the difference in densities, 1,000 minus 840 times that, that would end up being the tension force, because this is force upward caused by the buoyant force of the water. This is the force downward caused by the gravitational pull, and tension's the difference. So I might be able to show that down here. At any rate, when I end up doing this, it's going to be a little bit more. It's 0.735 newtons. So the tension in this case is 0.118 newtons. It's pretty light. So since this is rho plastic times V times G, I'm going to rewrite this down the bottom a little bit differently. So I would say density of water minus density of plastic that's the difference in densities times V times G is going to equal the tension force. Because that's a net force up, that would be the net force pulling down. I think this is probably a better way to do this because it relates back to the free body diagram. Anyhow, hope those help with the density problems. That's the last part of the examples. Ta-da!